Good afternoon, everyone. Thank you for joining this session. My name is Sima Iranmanesh, and I'm from Birmingham City University. In this session, I'm going to speak about a part of our research work on information extraction from a part of our research on information extraction from IFC data, which we used large language models and Graph Rag. So starting from IFC data, so they are standard languages for representing information about buildings, and also they are very commonly used in construction project and construction workflow. However, so speaking about the challenges, they are completely complex and highly structured, and in order to extract a specific information, we need to somehow find the information which are hidden behind deep references and multi-level nested relationships in these files. So, of course, there are some tools that, like BIM schemes that we can use, but they are usually need some expertise in these tools, and also they may need some query languages, some information about the query languages. So considering that many non-technical users may need some information from IFC data, or even the expert people may need some information quickly. So the question here is how we can extract information, or maybe focused information from these IFC files fast and in natural languages. So here is the Graph Rag and large language models that can help us in this regard. So large language models has great capabilities to parse structured data, and we call them Graph Retrieval-Augmented Generation, or Graph Rag. And how they work is that we have our IFC data, we create the knowledge graph, and we somehow feed this knowledge graph into the large language model, and we ask questions in natural language. So, and also this can bridges the gap between the complexity of IFC files and data, and any kind of data, and user-friendly querying. So how we use Graph Rag for IFC data is we propose a Graph Rag parsing technique that enables the natural language query response retrieval from IFC data, and our technique somehow consists of two steps. The first one is graph generation, and the second one is the large language model using the few shots. So in the first stage, we obviously use IFC model, and we created a structured graph from that. So let's look at it in more details, that how we create this graph, considering IFC files that have many entities, properties, and references. So in order to create this graph representation, we consider each entity to be as a node, and also there is an edge between two entities if there is some references between them. So you can see how this complex part of IFC file then transferred into a graph representation. So in the second stage, we prompted the large language model with few shots. To do this, we provided some examples to our large language model, and these examples contain the question, cipher query, the context, which is the expected answer from the cipher query, and also the expected answer that is in natural language. So this is the general pipeline that we had, and the large language model uses its pre-trained knowledge, uses the generated knowledge graph, as well as the of course, the query to extract the correct answer from the complex IFC data. So any input query for GraphRag, it created first a cipher query, it extract information from knowledge graph, and then the context or the result from the knowledge graph will be transferred into the natural language and will be shown to the user. So for the experiments, we used a small-scale building IFC model from the Building Smart public data. And the generated graph was a very large graph with 47,000 nodes and 82,000 edges around. And also we use a Neo4j desktop for graph storage. We use the GPT-4 OpenAI API for the large language model. And we also use IFC OpenShell in Python in order to extract information from the IFC file. So we created a question bank of 60 natural language queries and the expected answers. So these queries also had from different difficulty levels, easy, moderate, and hard. So we do our experiments, and here are a part of the results that you can see. I think they are very small, so we have them here. So as you can see that this technique somehow works on very easy questions. The questions like counting the elements, or also answering a very specific question, or like what is a specific property about element. But we had some answers which wasn't completely correct, but we can say that they were incorrect completely. For example, what is the building address? That you can see the expected response was the address is, let me open it. Yes, here. So for example, this is the address, and the second, the response from large language model is inter address here and the address. So this is, we don't consider it a problem with the large language model. In other words, we can say that if we update our IFC model in a way that it is more, how to say, pre-processed in a way that all the information are correct, we can see that in this stage, large language model can answer correctly. Or this is the same. So for example, so for the next question, what is the unconnected height of the roof space? So this is what we expected, but the large language model also brings the function that shows the measure of the result. And also in the correct answers, so for example, we expected to the large language model to somehow round the final value that it is showing to the user. However, it actually bring all the value with all the decimal points. And we also, definitely, we had some questions that large language model answered incorrectly. And from them, there were also some questions that coming from different hop relations in the graph. So for example, considering what is the specific feature of the wall connected to wall, I don't know, with name IFC wall 2, for example. So this means that the large language model needs to create a cipher query that considers a different hop, multi-hop connections in the graph, which it's not answering accurately. So in conclusion, so we explored the use of GraphRag with GPT-4o to extract information from IFC files using the natural language queries. So it was able to somehow access these BIM models and answer the questions somehow correctly, but we faced some challenges, obviously. So one of the challenges and somehow limitation was the somehow recognizing the correct entity names. So considering that a roof can be an element or it can be a space, so providing some information about it for the, for the large language model using the name entity recognition in future can help for this limitation. Or also another example for this could be, for example, in a building model, we may have IFC wall and also we may have IFC wall curtains. So these were some limitations that we faced about the entity. And also in future, we are the work that we are currently doing, which we are actually seeing more promising results. We are considering to first do more pre-processing on the graph, and we are somehow dividing the graph into smaller subgraphs in a way that each subgraph is considering a specific element, and we are also considering more focused information retrieval. So instead of considering all the IFC model and all the elements and features possible, we may only focus on the extracting information about walls, the connection, the features, and everything that is relevant to a specific focus subject. And so another, as I mentioned, another improvement could be the NER integration, which helps the large language model to answer more accurately. Yeah, thank you for listening, and you can exercise later.